Hello, and I wish I could be there in person, but thank you for the opportunity to share my research. I'm going to talk today about a method that I've been developing for creating automated avalanche terrain exposure scale maps. Uh, at the high level, this is a way to characterize avalanche terrain hazard using an existing classification scale that was developed in Canada as a way to improve communication with the public about avalanche terrain. And I want to recognize my co-authors, Håvard Larsen from the Norwegian Avalanche Forecast Center, and my supervisor, Pascal Hageley from Simon Fraser University. Before I get started, I just want to recognize that the study areas for this research are on the unceded territories of several Canadian First Nations. You can see the relative location of our study areas to some of these First Nations on the maps on this slide. So what is ATES? It's the Avalanche Terrain Exposure Scale. Was originally developed in 2006 by Parks Canada and Avalanche Canada. And the first version just included simple, challenging, and complex terrain. So it broke avalanche terrain down into three basic classes. There's currently a new version in development, which also includes non-avalanche terrain, which is class 0, as well as extreme terrain, or class 4. Our automated method is based on a digital elevation model and some kind of forest input data to characterize forest density. The first step is to calculate a potential release area model, which is essentially trying to capture avalanche start zones. And this is based on slope angle, wind shelter, and forest density. You can see on the map to the right, there's the yellow colors indicate areas with higher probability of avalanche release, and the blue and purple colors indicate areas that it's still possible but lower probability. The second step is to take the output from that potential release area model and input it into a runout model. The runout model we're using is called FlowPy, and it was developed by a research group in Innsbruck, Austria. It essentially takes each start zone pixel and simulates the potential runout out to a predefined alpha angle. So in this case, we're using 24 degrees, and you can see the blue colors are going to be lower alpha angles, so further out into the runout zone. And the hotter colors, the yellows and reds, indicate still avalanche zones that are closer to the start zones. The final step in creating the automated ATES map is to classify each of these input data sets using a series of raster classifications. And this is based on slope angle, alpha angle, the overhead hazard, and forest density. And the output has the same resolution as the input digital elevation model. You can see in this map, simple terrain is colored green, challenging terrain is colored blue, complex terrain is colored black, and extreme terrain is colored red. We don't use class 0 or non-avalanche terrain in the automated method because of the potential for artifacts in the input data sets to indicate that there's no avalanche hazard when in reality there could be avalanche hazard. So we're saving class 0 terrain for human-generated maps. In order to test this automated model, we used two different field sites in Western Canada. One is in Connaught Creek in Rogers Pass, British Columbia, and the other is in Bow Summit in Banff National Park in Alberta. We collaborated with ATES mapping experts from Avalanche Canada and Parks Canada to create 3 individual ATES maps, which you can see on the upper right of the slide. So each of these Avalanche experts created an independent map, and then they came together to create a consensus map, which we call the ATES benchmark map that you can see on the bottom. And this is based on all their combined experience from the areas. Here's a comparison of what our automated ATES map looks like compared to the ATES benchmark map. There's certainly differences. The human-generated map is based on manually drawing polygons in the terrain, so it's a little bit smoother. And the automated map is based on classifying each pixel based on the terrain characteristics for that specific location. But in general, the broad patterns are quite similar, and the overall accuracy of this map is 74%. So 74% of the pixels between the benchmark map and the automated map are the same. To compare the performance a little more against the human-generated maps, you can see in these bar charts, each one of the clusters is from the automated eights on the left, and then the 3 human-generated maps on the right, and it shows the accuracy for each eights class. So how many of the pixels for each class were the same for each one of these eights maps. And you can see that between the human maps, there's quite a bit of variation in terms of overall accuracy and also in terms of how accurate each person is for each class. And the automated map is similar, but you can see here that it has a similar level of accuracy compared to the human-generated maps as well. This is the same output for our Bow Summit study area. This area is a little bit simpler. It's a kind of a steep alpine face that then transitions into lower slope angles and forested terrain at lower elevations. So you don't have to deal as much with multiple avalanche paths coming from 2 sides of a valley. So the overall accuracy is quite a bit higher at 84% for this terrain. And again, just comparing the automated output to the human-generated maps, you can see there's quite a bit of variation between the human-generated maps, which are the 3 clusters on the right. And the automated map is a little bit more consistent in which class it performs better in. And again, has a very similar level of overall alignment to the benchmark map compared to each individual human map. To get a better sense for what the limitations are of the automated eights model, we tested it in Connaught Creek using 4 different DEM data sets as input. So we tested a 5-meter LiDAR DEM, a stereo digital surface model that's 10-meter resolution, the Canadian digital elevation model, which is available for the entire province of British Columbia, which is about 17-meter resolution, and finally a free global satellite digital stereo elevation model, which has a resolution around 26 meters. We were surprised to find that the overall accuracy of the eights classifications is really very similar for each one of these elevation models, despite the fact that there's obvious differences in their ability to capture small scale terrain features, which you can see in these maps on the right. And we think that that's largely because the eights classification doesn't require super high precision. The classes are quite broad, so the ability to accurately classify it by eights doesn't necessarily require very high precision mapping of small scale terrain features. And this is a huge advantage for us because one of the end goals of this research is to create large scale maps across entire mountain ranges and forecast regions in Canada, where high resolution data is very hard to come by and very expensive to generate. So in conclusion, automated eights classification is flexible for different locations, and we can change input parameters based on H benchmark maps or less formal feedback from local avalanche professionals. The accuracy is roughly equivalent to human mappers, and it has big advantages over human mappers in consistency between study areas, low cost to process large areas, and we're going to make the software open source so anyone could apply this scale across the world. For future work, we're hoping to utilize more remote sensing data sets like Sentinel-2 to have a better spatial resolution and temporal resolution of forest density. And we're also going to continue working with avalanche centers both in Canada and the United States to get more feedback on the mapping process and hopefully improve accuracy. Just want to thank the supporters of our research program, and I'd be happy to take any questions.